Tonight we'll be joined by Mr. Tom Blees. He's a researcher and author of Prescription for the Planet. Tom is also the president of the Science Council for Global Initiatives and sits on the selection committee of Russia's Global Energy Prize, which is one of the world's largest prizes, and it's equivalent to the Nobel Peace Prize for Power Technology. I have no doubt this award, within a few years, will surpass the Nobel Peace Prize, but I guess that's proven, waiting to be proven, but I'm feeling pretty confident of it. You can learn more about Tom Blees, his fabulous book, and his work via his website, prescriptionfortheplanet.com, and also at thesciencecouncil.com. Now, tonight, I'm not going to go over those again, but just if you have any other questions, Google Tom Blees. Tonight's program will be broken down into two segments. The first hour will be an interview with Mr. Tom Blees, followed by up to another half hour of open lines. Now, Tom has agreed to take a couple calls after the hour interview, but considering it's the holidays, I don't want to keep him away from his family all night long. So when you do call in and ask questions, please try and keep them concise and to the point. The call-in number to tonight's show is 760-542-3929. That is 760-542-3929. And on to our guest. Tom, you're on the air.
Thanks for having me. Looking forward to this.
Thank you.
And don't worry about keeping me from my family. I'm at home, so all is well.
Then I'm going to hog you to the full time maybe. No. Well, we talked yesterday, and I did. I took your time up for, probably 45 minutes, and it was a never-ending information stream of wow. That's my catchphrase, wow, and you're very impressive. Can you tell us a little bit about yourself and Prescription for the Planet?
Well, I didn't set out to write a book about how to solve the world's most intractable problems, really. I'd started a nonprofit organization to drill water wells in villages in developing countries. And in trying to raise the money for it, I decided that I would write a novel, a political novel that would have the background of the main character as this water project. And so I wrote this novel, and it was about a fictional American president. And because I was writing about this president, I had to write about, something about his various policies. So I thought, I got to write a couple paragraphs about his energy policy. And I started trolling what was then the early days of the internet, and found out about some technologies here and there that I'd never heard of before, and I realized that they could be used synergistically to solve an incredible array of problems, and that started a 10-year kind of divergence from my novel. And resulted ultimately in my book, Prescription for the Planet. And of course, during those 10 years, I learned about other technologies, and so ultimately the book focuses on three technologies that can make a revolutionary difference in the life and well-being of everybody on the planet, and deal with some really serious problems that we have staring at us, like climate change, water supply issues that are going to be rearing their heads as our population continues to expand. And so, ultimately, I wanted to put it all together in one comprehensive and yet quite easily readable book for the public, because these are going to involve changes that are going to entail decisions that are very difficult for politicians to make, because, for one thing, it would completely transform our energy infrastructure. And energy industries are the most powerful industries on the planet, and they won't go quietly into that good night. So I felt that the only way that we could get politicians to make the necessary decisions legislatively and policy-wise would be to educate the public about the fact that we can actually solve these problems and how we can do it, to put pressure on the politicians. I'm happy to say... Go ahead.
If we were to list out the problems, you mentioned climate change, water, and there's a few others out there that people may not quite fathom, such as I know you have in your book you address landfills and what else is there? Because your prescription for the planet covers all of them, and it, like you said, it synergistically fixes them.
Well, part of the reason why a proposal or a prescription like this can affect so many areas is because all these things are so intertwined. For instance, if you can supply abundant energy to the entire planet with essentially limitless fuel that's already at hand, then you begin to solve an incredible array of problems. For one thing, you start solving the problems of warfare that is caused by people's competition over energy supplies. You likewise go a long way towards solving the problem of water supply for another 3 billion people, which is going to take a tremendous amount of desalination, which is going to take a tremendous amount of energy. So the energy source is a huge piece of the picture. Another one is recycling. The recycling systems that we have in place today in developed countries are woefully, let's just say they're in their very early and rather poorly developed stage. What we need is a system of solutions that don't require people to be conscientious. And I think what you see if you read a lot about renewable energy and people's ideas about how we have to change our society so that we can have enough energy and not be damaging to the environment, very often, probably much more often than not, we find people appealing to the virtuousness of humanity and sometimes proffering ways of behavior modification and that sort of thing. To my mind, if the proposed solution to a problem depends on human behavior being something other than self-interested, then it's not a solution at all, because you're only going to find a minority of people who are extremely conscientious in the first place.
Mm-hmm. What do you? So we've got these problems, and another problem is the nuclear waste that's piling up all over the world. How do we fix it? What do we do?
The nuclear waste piles are actually very small. People make it sound like it's really piling up, but there's really not that much of it. The way that we solve the nuclear waste problem is we employ a technology that can burn nuclear waste as fuel and eliminate the million-year storage problem. It might not technically be considered a million years, but the problem with nuclear waste that is very distressing to people is not that we can't safely store it somewhere for a while. The problem is that we have to safely store it somewhere for hundreds of thousands of years. Now, there's a technology that was developed at Argonne National Laboratories in the 80s and 90s called the integral fast reactor, and it's a type of nuclear reactor that can burn nuclear waste as fuel. And if we deploy these reactors, which are extremely safe and extremely proliferation resistant, they've been designed to be proliferation resistant. The safety factor is absolutely phenomenal. If you run worst case scenario tests, which they've done, where the reactors are operating at full power and the control rods are out and all the operators die and you lose your coolant flow, the laws of physics themselves simply shut the reactor down, and they don't even do any damage to the reactor, you can come back later and start it up again. So, so if you take the probabilistic risk assessment figures, which what they call PRA. PRA is a science that's quite advanced, and many technological systems that have any danger element undergo probabilistic risk assessment, so that you can try to figure out, okay, is this too dangerous to deploy, and just how dangerous it is. So they've done very detailed PRA assessments for the PRISM reactor, which is the commercial version of this type of reactor, the integral fast reactor, that General Electric now is working on. And they gave these to the Nuclear Regulatory Commission, and the NRC pretty much signed off on them. And so I looked at the PRA figures, and it's interesting when you look at risk. You look at a nuclear reactor, say that the PRA figures say, well, you're going to have a meltdown once every 1,000 years. Well, that sounds absolutely safe, but you have to figure out, well, what if we have 1,000 reactors? That means that we're going to have a meltdown every year, and that's absolutely not acceptable.
It's insane.
So what we try for, the goal is to have reactors that are so safe that even if you produce all the energy that the planet needs, not just the electricity, but all the energy that the planet needs, how often are you going to have a meltdown? And so I took the PRA figures for the PRISM reactor, and I figured out how many reactors we would need to power the entire planet in the absence of any other type of energy system. And then ran the calculations to figure out, okay, if you had this many reactors, you'd have to divide that number by the PRA. How often could we expect a meltdown? And the number was once every 450,000 years, which is just astronomically improbable. It's several ice ages previous. Neanderthals disappeared, 60,000 years ago, I think. So so essentially, it's as close as you can get to fail-safe.
That's amazing.
And you know, from a proliferation standpoint, the fuel cycle, the entire fuel cycle, is always keeps the fuel in such a condition that it can't be handled. It never separates out plutonium or uranium, and since we can burn nuclear waste, if we started deploying these reactors at the pace that I propose in my book, we would actually use up all of the world's nuclear waste in about 3.5 years. Really?
Now, how would that apply to the nuclear stockpiles across the world? How long would it take? Because now I was under the impression that these would not only they'll burn depleted uranium, but actually the enriched bomb or nuclear, bomb grade material. How long did you do figures on that? As far as, we've got this nuclear material that's, it's a mad scenario where mutually assured destruction is the goal. How long can we burn all that stuff instead of blowing each other up?
Well, it'll provide energy for a long time, but what we really want to do is we want to take that weapons-grade plutonium and get it into a form that can't be used for weapons anymore. There are a couple different ways to do this, and back in 1993, President Yeltsin and President Clinton agreed to dismantle several tens of thousands of nuclear warheads, and each side would then have 34 tons of weapons-grade plutonium to dispose of. So the presidents asked two of their top scientists to suggest how to get rid of this. And Russia's top scientist in the field, Dr. Evgeny Velikov, who's a member of the Science Council for Global Initiatives, suggested that we use fast reactors similar to the one that the integral fast reactor. And Russia has a fast reactor that's been operating for many years, and it's very reliable. and he knew that you could take this weapons-grade plutonium and very quickly contaminate it with fission products so that it would be useless for weapons. You could take the 34 tons of plutonium that Russia had, put it in a pair of PRISM reactors, if we would build a pair of PRISM reactors, and basically spike it with fission products that make it unusable. It would take about a year and a half. Now, the United States, because we were getting ready to kill our fast reactor program, didn't recommend this system. They recommended another system that's substantially less efficient. It's called mixed oxide fuel. And in order to utilize that, we have to build a mixed oxide fuel plant, which we're now building down in South Carolina at a cost of about $10 billion. And it's going to take until after 2030 to take care of this 34 tons. Meanwhile, the U.S. and Russia are dismantling even more nuclear weapons with the New START treaty, which hopefully will be ratified by the Senate. And so it's going to take even longer. So we're going to spend $10 billion and take over 2 decades to do something that could be done in a year and a half with a pair of PRISM reactors, which would cost considerably less than $10 billion. So, we're into a political crazy scenario here where we're pouring billions of dollars into a system that's far less efficient at removing weapons-grade material than what the Russians are going to do.
Now, you went over some spectacular information number-wise with these integrated fast reactors with me yesterday. One was the efficiency of the reactors compared to the normal reactors that we usually are familiar with. 2, let's see, it was their efficiency, and then also you went over the numbers as far as not having. You told me yesterday that we won't have to mine any uranium or anything for several hundred years. Can you elaborate on both of those?
Sure. The reactors that we have now are called light water reactors, and the fuel for them has to be enriched. What they you hear about fuel enrichment? It's a very energy-intensive process. And basically what you're doing is you're taking natural uranium, which has only 0.7% of what we call fissile material. And in order to make it work in a reactor, in a light water reactor, you need to get that up to about 4 to 5%. So what you do is you take that 0.7 from several pounds of uranium and you put it into another pound until you get it up to 4 to 5%. This leaves you, for every pound of fuel, with about 9 or 10 pounds of what we call depleted uranium, where that fissile material has been mostly taken out, although not completely because the system isn't that efficient. So because we've been using light water reactors for so many years, we have vast stores, literally millions of tons of depleted uranium around the world, for which there's very little use. Basically, you've heard about where we use it. We use it to armor our tanks, and we use it to shoot at people in our wars over oil. But it could be much more profitably and humanistically used as fuel for these reactors. Whereas a light water reactor only extracts about 0.6% of the energy that's in natural uranium. These fast reactors can utilize 100%. So they're 160 times more efficient than the nuclear reactors we use today at extracting energy. And of course, the ones we use today are phenomenally efficient at getting energy from a small amount of material. So you can imagine something that's 160 times more efficient. So basically, we would be able to, once we use up all our spent nuclear fuel and once we use up all our weapons-grade material, we could start using depleted uranium and just putting it in these reactors. And there's so much of it already out of the ground that if we powered the entire planet only with this type of reactor, we could do so for almost 1,000 years before we would ever have to mine uranium again. And of course, in 1,000 years, who knows what our energy systems are going to look like. So essentially, our fuel, for all practical purposes, is free for the next 1,000 years.
For the entire
matter
world.
Matter of fact, it's better than free because people would pay to get rid of it. So
and this is for the entire world.
For the entire planet. And just to give you some graphic idea of how energy dense this is, if you consider all the energy that a person would use in a normal lifetime, say 75 years, for not only electricity, but for heating and cooling, for transportation, for the energy that goes into everything you consume, your food, your consumer goods, you could extract that much energy from a piece of depleted uranium the size of half a ping pong ball. And the waste that you would get out of that material would be about the size of a ping pong ball. So, and the waste, unlike the waste of today from light water reactors, would only be radioactive beyond background levels for about 300 years. And it would be in a glass form that would not allow it to leach into the environment for thousands of years. So thousands of years after it had already diminished in radioactivity to far below background levels, would it ever be in a position to even then begin to very slowly leach into the environment. So basically you've solved your waste problem, and you've solved the problem of fuel, and you've solved your safety problem. And because most of the emissions associated with the nuclear life cycle, which are they're reckoned by the IPCC, the International Intergovernmental Panel on Climate Change, who studied this issue, they reckon that the life cycle carbon costs of nuclear is about the same as wind power. But most of the life cycle carbon costs of nuclear power comes from mining and enrichment, which you wouldn't have to do anymore. So essentially the life cycle carbon costs associated with building these new reactors would be whatever the carbon cost is of the cement that goes into them, pretty much. And even at that, there's a new type of cement that uses magnesium silicate that actually takes carbon out of the air. So you could even have a negative life cycle carbon cost if you use that kind of concrete. So essentially, you're solving the energy problem. If we use this, you're solving all the problems associated with nuclear power, and you're solving the energy shortage problem for every nation on the planet. I mean, literally every country could be energy independent with more energy than they can shake a stick at, than they could care to use, and this has tremendous ramifications for economic well-being and standard of living and everything else, as I'm sure you can imagine.
Oh, it's mind-blowing. I mean, it's truly mind-blowing. This would, in my eyes, turn the entire world into the first world, and it wouldn't be this country is better than that one. It would be equality. I want to touch on the waste aspect. Now, a regular reactor, a white water reactor, you have waste, and in these integrated fast reactors, can we go over precisely when you have the fuel rods in the integrated fast reactors, when they start wearing, how long do they last, and then what do we do with them when they start tiring out and they need to be replaced exactly? Because you gave me a couple different options that were just amazing.
Okay, well, after when you burn fuel in a nuclear reactor, because the atoms are splitting apart, you end up with a whole array of new elements. And some of these elements impede the flow of neutrons and so act as what they call a nuclear poison. And when those nuclear poisons build up to a certain degree, the reaction can't sustain itself. So you have to pull out some of the fuel and replace it with new fuel. Now this happens with light water reactors just as it does with fast reactors, and when it does, we just take the what we call the spent fuel, and we just set it aside. And that's our nuclear waste problem that everybody talks about. It's equivalent to taking a log and throwing it in the fire and burning off the bark and throwing away the log, because you've taken out just a little over 0.5% of the available energy in it. Now with a fast reactor, you get a much better burn up on the first pass through the reactor, but eventually you have to replace that fuel too, because you do get a buildup of fission products. And so about every 2 years, you would take 1/3 of the fuel out of the reactor, and it would then be put through a very simple process, a reprocessing system called pyroprocessing. That's essentially an electro-metallurgical process that goes on every day in, say, aluminum factories. And in this process, you would take out what are called the actinides. That's all the elements higher on the periodic table than actinium, which include uranium and plutonium and americium, neptunium, and those would be incorporated into the new fuel rods. And all the other fission products that don't have as long a half-life, in other words, that would be radioactive for a much shorter period of time, are then encased in glass, and that's your nuclear waste that you get out of a fast reactor, and that will, like I said, be radioactive below background levels within about 300 years. And the glass itself, it's rather like onyx, borosilicate glass, and it's meant to be a non-leaching substance. So even if you took that radioactive material in that glass and buried it in the ground unshielded in an aquifer, it still couldn't get radioactive material into the aquifer because it would be encased in the glass. Now, obviously, you're not going to do that. It's much more sensible to put it in a place where it's going to be completely gone, like in salt domes or something like that. But all the long-lived elements, that they just go back into the new fuel rods. And 2 years from then, when you pull out another third of the fuel, you would put that first third back in. The fission products only comprise about 5% of the fuel that comes out, and that 5% you replace with depleted uranium or with spent nuclear fuel from light water reactors. So essentially you're just feeding in a very small amount of material. I forget exactly how much it is, but it's maybe a gallon or something for a 300 megawatt reactor. It's a very small amount.
Now, from what I've read, Japan, China, and Russia all have integrated fast reactors or prism reactors, but the technology was created in the United States. What happened there? Why it didn't go anywhere?
No, those countries don't have prism reactors. They have Russia has one fast reactor now. They did have another one previously, which they had in the Soviet Union back in the 70s. They opened it up in what is now Kazakhstan. And they built that with the specific goal of creating a dual-use power plant that would not only produce electricity but would desalinate water. So they did the world a favor by amply demonstrating the practicality of using fast reactors for desalination and electrical purposes. China, and it should be said that the fast reactor that Russia has now, the BN600, has some substantial differences from the prism reactor. it uses oxide fuel as opposed to metal fuel, and metal fuel is far superior. But the concept of the fast reactor is the same. China recently fired up their first experimental fast reactor, and Russia is going to build two BN-800s for China. Japan has a fast reactor at a place called Manju, which is also an experimental reactor. It also does not use metal fuel. India has a commercial size fast reactor, 500 megawatts, that's going to be coming online probably in about a year. And they also don't use metal fuel. However, they want to. It's just that they haven't developed the metal fuel to the degree that the United States has yet. They're working on it, and they plan to convert their fast reactors to metal fuel as soon as they get the bugs worked out. We could, of course, help them work out the bugs, and part of the goal of the Science Council for Global Initiatives is to create a political framework so that the United States could and would willingly share this technology with these other countries so that we could have the ultimate in safety and efficiency and begin to make this transition to a world of energy abundance. Okay,
but now the technology was created in the United States. Was there political pressure, or because if I'm not mistaken, the original program ended in the mid-'90s. What is the change of heart? Because it sounds like they're going forward with the technology now, but in the mid-'90s they just stopped.
Well, yeah, and I mean, I hope they go forward with the technology now. We're working on that, trying to get the United States to finally build the first full-scale prism reactor and the recycling portion that goes with it to make it an integral fast reactor. Because the point of the integral fast reactor, and the reason for the word integral, is that you would have a small recycling facility at each power plant, so that when uranium or plutonium goes into it, it never comes out of it. It only comes out as fission products, which are different elements that are encased in glass. So what happened was in 1994, well, in my book I deal with the politics of it, and a lot of people have suggested to me that the fossil fuel industries were behind killing this project. But you know, as feasible as that sounds, or as predictable as that might sound, I find it difficult to consider that there was such a conspiracy, because it looks more like, from the evidence that I've seen, that it was a question of political self-interest and short-sightedness, a notion that this was better for the budget, just a lot of really kind of myopic decisions, which are typical of many that are made in Washington, to kill this project. And unfortunately, it was pretty much buried for, well, until my book came out. Even though some of the scientists who worked on it would write about it or be interviewed periodically, but the general public really wasn't aware of it. It wasn't making its way into the public consciousness until recently. And I'm happy to say that it is now, so hopefully we'll get back on the stick. But whether the United States sees fit to do this or not, other countries are they're going there. Everyone in the nuclear power industry understands that fast reactors are the reactors we'll use in the future. South Korea and India in particular are working on metal-fueled fast reactors, so it's only a matter of time. And it would be a shame if the United States, having developed this technology to this point, would continue to refuse to share it with these other countries. I think that's changing. It looks like it is.
That's what I was I find that interesting because we developed the technology, but it looks like the Eastern world is leading the charge in getting it implemented, which, you know, I want to cheer them on. I think it's wonderful, and I see no other way but to follow in the U.S. because the rest of the world's going to leave us behind. Now, I wanted to move on. I think we covered the fast reactors in great detail. Actually, I'm really happy. You have two other technologies, and I wanted to specifically, because both of them are somewhat intertwined with vehicles, the vehicles we have now as far as fuel. So can you go into detail on the plasma recycling and how we can use that to power? I mean, it's got a myriad of, I mean, it really does solve problems, but it also will power our vehicles and change or put us off of fossil fuel. So if you could touch on that a little bit.
Sure. One thing about plasma converters is the amount of I guess I can get to the quantities that are involved in terms of replacing all our gasoline and that sort of thing a little bit later. I'll just explain a little bit about what plasma converters are right now.
This question is odd because I'm not trying to cut you off. It's almost hard asking the questions because in reading your book, what I've read of it, this is, for lack of better words, it's almost like Leonardo da Vinci or something, or it's incredible. Every single problem that we experience in our daily lives, you have solved in one single book. And so,
my God, you make it sound like a religion.
I was sitting there going, my God, this guy has literally, your book's easy to read. It was in layman's terms, which, hey, it works for me. And it every question I had in my mind when you would you'd start talking about something, you would counter it immediately, and my questions or my hesitations were answered. So I don't mean to leave the questions too broad. So please continue.
Okay. Well, the plasma converter is the ultimate recycler. It would allow us to eliminate our entire recycling and landfill infrastructure, and we could throw everything into the same dumpster. It doesn't matter if it's asbestos or old food or poopy diapers or
oil,
nerve gas, drain oil, old tires, whatever. It can all go in the same dumpster. And this is one of the things I was talking about where we can't rely on human behavior. I used to live in an apartment complex, and we had our recycling containers out in front, and people would dutifully throw their paper and their plastic and cans and their glass into these recycling containers. Some of the people, but if you open up the dumpster where everything else gets thrown in, you'd see there was all kinds of plastic and glass and everything in there because a whole lot of people just don't care. And so in order to really be efficient and really do the recycling job right, you have to have a system that just doesn't depend on it, where you're going to be able to get away from having all these separate bins in your kitchen, and you're just going to throw your garbage in the trash can. The way it works is it uses plasma torches, and plasma torches are used in industry. They call it lightning on a stick. If you've got a 12-inch thick piece of steel that you want to cut, you use a plasma torch to cut it. It generates heat that's hotter than the surface of the sun, and so what you do is you essentially take your garbage and you run it through these plasma torches, and what it does is it separates out the carbon and oxygen and hydrogen. It does a molecular deconstruction, if you will, so that, for instance, asbestos, which is made up, I forget what the elements are that comprise asbestos, but it breaks it down into its constituent elements, and everything else it breaks down into its constituent elements. So it's been used to dispose of nerve gas and things like that are really nasty. but it essentially breaks all these things down, and you end up with what they call synthesis gas, which is made up of carbon, oxygen, and hydrogen. And then you end up with a molten slag that comes out of it, from which you can very easily recover all the metals. And what you have left after that, you can use in several different ways. You can spin it to make rock wool, which is an extremely efficient insulation, better than fiberglass batting. Coincidentally, rock wool is also really good for soaking up oil spills. So if while we're still using oil, we could take this rock wool, we could dump it in an oil spill, and when you pick it up and it's full of oil, you throw it back in the plasma converter and you just run it through. And the oil would be deconstructed into its constituent elements, and you'd get more synthesis gas from it, and then you can make even more rock wool afterwards. So you could also make building materials. You can make bricks and tiles and road building materials. So essentially you can use everything, and the most valuable parts of what you're getting are the metals, which you've been able to recover, and the carbon, oxygen, and hydrogen, which, of course, are the three elements that comprise hydrocarbons. And from this synthesis gas, you can make anything that we now make out of oil. So you can make plastics, you can make liquid fuels, ethanol, methanol, jet fuel, even gasoline. You can make tires. So basically, you can take garbage or agricultural waste, any kind of waste product, basically, and deconstruct it and make everything we get from the petrochemical industry today. And as a matter of fact, in my book, I call this chapter Exxon Sanitation Incorporated, because it would make a lot of sense for the oil companies, who are going to be put out of business by these technologies, to get into the garbage business. They're the ones that are the experts at manipulating hydrocarbons, and they have a lot of the equipment that you would use to make the plastics and tires and everything else out of the syngas. It would be entirely logical for them to get out of a dying industry, which ultimately petrochemicals are a dying industry because we're going to run out of oil, and we're not going to need them anymore, and get into a growth industry, which is garbage, because if everyone on the planet is raising their standard of living, there's going to be a lot of garbage. There's already a lot of garbage, but there's going to be a lot more. So
what's the byproduct? What's the downside? There's got to be a downside. There's always a downside.
Well, there isn't any downside. You're using all the material. I mean, I suppose you could look at the downside as we're going to end up with a whole lot of excess building materials, because, even if we sell it really cheaply or give it away, you're going to get a lot of building materials out of this.
And you had a creative way to solve that, I believe.
Yeah, well, that has to do with the destruction of coral reefs around the world. It's a big problem, partly due to acidification of the oceans, partly due to overuse and misuse, where reefs are dynamited and dragged and otherwise broken up. And reefs are very important to the livelihood of people who live along the coast, especially in developing countries, where the small fisherman works out on his little boat and goes out every day and tries to catch some fish, and if the reefs are unhealthy or being destroyed, that's bad news for starters. But in many places around the world, the majority of places around the world, the continental margins, the shallow area along the edge of the continents, are essentially rather deserted. Oftentimes they're just mud flats or sand flats, and they have a minimal amount of vegetation and a minimal amount of sea life. Yet if you sink a ship in any one of these places, pretty soon you find sponges growing on it, and in the tropics, corals, barnacles, all sorts of creatures, sedentary creatures, come and attach themselves to it. They get there, of course, because their plankton is floating by, and when there's an environment where the plankton can thrive, it'll attach itself. And then once that happens, of course, there's a lot of nooks and crannies in this sunken ship, and so shrimp start moving in, and you end up with a little ecosystem. Basically, a sunken ship becomes a reef. Now, recognizing this, there's a company called Reef Balls that actually makes concrete spheres with holes in them for fish to hide in and that sort of thing. And they dump these on areas where reefs have been damaged, or they dump them in areas where there are no reefs, where somebody wants a reef. And sure enough, pretty soon it becomes a reef community, because there's no shortage of inhabitants for such places. The limiting factor is the fact that there aren't enough reefs, not the fact that there's not enough fish to fill the reefs. So if you increase the number of reefs, then you increase the number of fish and sea creatures that live on the reefs. And if you can do that, especially in developing countries, you increase the base for fishermen's livelihoods, and you provide more food to people, and essentially make you increase the fish carrying capacity of the oceans. Now, because if we're processing all of our garbage with these plasma converter systems, we're going to have so much more of this material for building materials than we need. We could simply pour the slag into reef ball molds, and with the advice of marine biologists as to where to locate them, start scattering them along the margins of our continents, and taking what is going to be pretty much a waste product, or at least a very low-priced product, and tremendously increasing the carrying capacity and the biological diversity and health of our nation's seashores, every nation's seashores. And of course, in the United States, that would translate into new sport fishing business, which we've already seen. The Reef Ball Company has created reefs. I think there was one off New Jersey that they just went in and made a reef and developed a whole sport fishing industry in a place that never had one before. Yeah, it's kind of one of those unintended consequences of using this technology that we could really help out the oceans at a time when ocean acidification is a big problem, and unfortunately, before we can get climate change under control, it's probably going to get worse.
So we can get out of these plasma recycling facilities, we can get syngas, we can get more building materials than we could ever dream of using, to where we have to actually make reefs that do another thing, which create more fish life, which feed more people. Are these plasma? Now that all sounds really good, but can these plasma recycling centers, can they actually sustain themselves? Do they produce enough energy? I mean, what is the? It seems like a plasma. I'm thinking about a plasma cutter that takes a lot of power. What's the efficiency like with one of these centers?
Well, there are a couple that have been running in Japan now for some years. They're not real large, but they process sewage sludge, municipal solid waste, what we call garbage, and shredded cars. And they, instead of making plastics or liquid fuels out of their syngas, they simply burn it in turbines to produce electricity, and they sell the electricity. Now it takes 20% of the electricity that's produced feeds into the torches to keep the torches going, and 80% feeds into the grid. So that they're basically 80% efficient.
That's incredible.
So yes, they definitely can sustain themselves. Now, in a world where we're running integral fast reactors, we could use all of the output of syngas for plastics and other materials, and simply draw the energy out of the grid if we wanted to do that. But you can do it either way, or you can combine them to just produce just enough electricity to run it, and then use the materials for something else.
Now, I read in your book that these recycling centers could be fitted onto trucks, as in, like, if I read it correctly, between two semi-trucks, you could have a portable plasma recycling center. Is that has that been done? Or?
It would be. Right now they've put a couple of them on Navy ships because garbage is a big problem for the Navy. When you have an aircraft carrier, for instance, it's like a floating city, and they produce a lot of garbage, and they don't want to carry it around until they come back to port, and they don't want to dump it into the ocean. So you can get a quite small footprint with these things, and it would have been really practical if we could have had some on some semi-trucks when Katrina hit New Orleans, because that was a tremendous cleanup job that could have been greatly aided by some trucks with plasma converters on them, because essentially you could have come in with front loaders and bulldozers and just shoved all this stuff into plasma converters and made fuel out of it. We're unfortunately not quite there yet, but we're getting there. There's also a brand new application for the plasma technology that I'm working on right now with a company that I'm associated with, and this would allow us to use the plasma technology to convert CO2 streams that are now vented to the atmosphere, and make the CO2 into liquid fuels like ethanol or methanol very cheaply, extremely cheaply. Now, you get almost pure CO2 streams vented to the atmosphere from ethanol plants and also from natural gas power plants. And so what this would do is it would allow every natural gas power plant and every ethanol plant, well, it would allow the ethanol plants to produce about 66% more ethanol than they do now. It would allow natural gas-fired power plants to all become liquid fuel plants. And the liquid fuel that they would produce would actually be more valuable than the electricity that they produce. So this is brand new. This wasn't in my book, but it's just being developed now, and by next year we should have the first commercial scale ones up and running.
Wow. That's
amazing.
amazing.
So between the syngas that you can get from all your garbage and the syngas that you're going to be able to get from power plant, natural gas-fired power plants, you're going to go a long way towards producing enough fuel to run your vehicle fleets. But the third technology in the book that I wrote about is using boron as a fuel. And there is another technology that I didn't write about in the book because, frankly, I didn't know about it at the time, and that is using ammonia as a vehicle fuel, which we already know how to do. The boron hasn't been developed. It's not really being worked on except kind of peripherally by Oak Ridge National Laboratories. But the ammonia fuel system is something that has already been rudimentarily developed and is in the process of being developed for over-the-road trucks. Because you can build an ammonia power engine very similar to a diesel engine. And ammonia just simply acts as a carrier for hydrogen, so that you can produce your hydrogen from electrolysis, splitting water, all of us did in chemistry class in high school, I'm sure, where you take the H2O and you split the H off from the O, and then you combine the hydrogen with nitrogen from the air through a process that's very well understood and used all the time, and you produce ammonia. Now, a lot of people have talked about the hydrogen economy and how that's the way we have to go, but a lot of people have become disabused of that notion because, for one thing, hydrogen is really difficult to deal with. It's explosive. It leaks out of everything. It would take literally trillions of dollars to build the infrastructure. There are more problems than you can shake a stick at. But ammonia we know how to use. It is a way of carrying hydrogen around by hooking three atoms of hydrogen onto one atom of nitrogen, and farmers use it all the time, and that's why the first ammonia-powered engines have been built for tractors, because the farmers have ammonia there, so when they need to fill up their tractor, they just go over to their ammonia tank that they normally use for fertilizer and fill it up. The good part about this, well, there's a lot of good parts about this. One is we know how to use it. Two is we already have an infrastructure in place, which would obviously have to be greatly expanded if we start using it for our cars, but it's completely doable. And the other is that it would allow us to use all the electricity that we get from wind and solar power, which is so problematic to integrate into the grid. We wouldn't have to integrate it into the grid. We could simply use the electricity for splitting hydrogen and oxygen from water, and then use the ammonia that we could make at all our wind farms and solar farms to power our trucks and cars.
Now, could you go into detail? Could you go into detail regarding, for our listeners that don't know, why wind power? Because there's a large push to go to your technologies that you've covered. They seem like you've got the big oil that's wanting to hold on to their fossil industry, and then you've got these very green technology people that say no, we want to go strictly with wind and we want to go strictly with solar. Can you explain why wind and solar just don't cut it for a society like ours, where we have basically the industrial, we are the industrialized age. It never went away, it just evolved. So what is wrong with wind and solar as far as the grid is concerned?
Well, the grid operators have to always balance supply with demand, and demand, of course, fluctuates greatly. And you want to be able to load what they call load balance as easily as possible, and it's easier to do that with systems like hydropower and gas and coal, where you can kind of ramp up and ramp down the systems. When you have wind power, you have an extremely erratic energy source, electricity source. So you've got this spikes and dips running into your system all the time, and it just makes the grid operators tear their hair out. To some extent, you have the same problem with solar, because of course you know that you're going to get a peak of solar around noon or 1 o'clock, and you know that you're not going to get it at night. But that also fluctuates greatly when clouds go over, for instance, and so there's this constant battle that the grid operators have, and every time you add a wind or solar system into the grid operators just kind of roll their eyes. So in order to try and deal with this, the proponents of these renewable systems, they propose that we build what's called a smart grid, and use new technologies to essentially try to iron out some of these bumps. Now, the estimates for how much it would cost to build such a smart grid, which has never been built yet, so it's it's somewhat theoretical. Obviously, our grid could get a lot smarter than it is. The estimates are it would take from $1 to $2 trillion to do it in the United States. Now, I would much rather take a portion of that $1 to $2 trillion and just build ammonia plants at all the wind and solar farms, because for one thing, that would obviate the need for building huge new arrays of power lines, which nobody seems to really want. The same people oftentimes that are clamoring for more wind and solar, they don't want a windmill in their backyard, and they don't want a power line going across their land. So, theoretically, it's a wonderful thing. As a practical matter, there are much better ways to do this. We don't need them to be integrated into the grid at all. Let's just make fuel, because if we make fuel, we're going to be using less fossil fuels if we make ammonia instead.
Wow, that makes perfect sense. It's incredible. Now, the ammonia, I just wanted to clarify that, and you did beautifully on that. The ammonia, from talking to you yesterday, they can convert right now. They can convert diesel engines to that. Can they not? Have they done that?
Yeah, it's being done. I forget how much it would cost exactly, but as a practical matter, as this technology catches on, you would probably just see, engines specifically made for ammonia burning, because it takes time to integrate new energy systems, no matter how ready they are for prime time. But yeah, the early ones have been regular diesel engines that have been gone through a conversion process, which wouldn't be all that expensive, I don't believe. But like I say, these are all these technologies are pretty much cutting edge technologies. So the first challenge is to look at them and figure out, okay, how can we use this, and then start building the first ones, which we have done already with integral fast reactors. We have done it with ammonia engines. We have done it with plasma converters, but none of these three technologies have made it into the mainstream yet. So I think what we'd see is we just probably see our large trucking fleets converting first, because it would be the easiest from an infrastructure standpoint. For instance, what we're looking at now is putting ammonia filling stations at truck stops up and down the I-5 corridor, the Interstate 5 corridor between Seattle and San Diego. There's a huge amount of truck traffic that runs up and down the I-5 corridor, and many trucking companies just run on the I-5 corridor. So if those trucking companies converted their fleets to ammonia-powered engines, a dozen truck stops between Seattle and San Diego could service all those trucks. So it'd be a way of very easily and at a very low cost initiating this process, and then you could branch out from there. And ultimately, people who want to have ammonia-powered cars would be able to do so. And at first, they'd just be filling up at truck stops. But ammonia is not that difficult to move around and to store, so there would ultimately be gas stations that would just have ammonia tanks, and you could fill. So
let me ask you three questions based off of the ammonia. Now, just so you know, we are over an hour, so we've covered a lot. I actually want to keep you on the line, so because this is so fascinating. The three questions. One, have they done any applications into jet engines for airplanes with ammonia?
No, not at all. And there's really no need to, because we can make jet fuel from the syngas that comes off of plasma converters. So that's not really an issue. There would be plenty of syngas for that.
Okay. Now that just to clarify, the syngas, because I believe I read that there's a plant in Pennsylvania that's making ethanol for $1 a gallon. Is that correct?
There's a company called Coscata that was funded by General Motors and a couple of investment groups that did their experiments in Pennsylvania to determine the most practical way to produce ethanol from garbage using plasma. And their experiments have now resulted in plans for the first very large-scale plasma converter to make ethanol. And they figure the price is going to be, I believe the price is going to be around $1 a gallon.
Incredible.
And it's in the planning stages right now. I believe they're going to build it in Alabama.
Okay. Now, that answers that question. I mean, it's incredible because I just filled up my car the other day. I think it was $3 a gallon. So definitely.
Well, I'll tell you, when we start making liquid fuel from the CO2 streams coming off of these plants, it's going to be very cheap. Very cheap indeed. Considerably under $1 a gallon to produce.
Wow. That's just incredible. Okay, so on to the ammonia, where you explain why solar and wind will not work very well with grid integration now, because they're going to need a smart grid. But have y'all figured out what the baseline price per gallon for the ammonia would be? And then if we could compare that to, since diesel engines will somewhat, with alteration, I know we're going to need to create specific engines, but what's the power, the energy in ammonia compared to just regular fossil fuels, and the cost per gallon?
Well, the cost per gallon for ammonia is going to depend on what you use to make the ammonia. And nowadays we use natural gas. We strip the hydrogen off of it. And then, of course, we end up venting a lot more CO2. If we used electricity from integral fast reactors to split the water, then basically you'd be able to do it like this. When you have a reactor, the reactor is perfectly content to run full power 24/7. But of course, electrical demand it fluctuates, and we have peaks at around 5 to 6 o'clock when people get home from work. Peaks during the day when it's really hot, when people use a lot of air conditioning, that sort of thing. So what we have to do is we have to have sufficient energy generation capacity to meet the peak demands. Now, what we do now is we have hydro plants that spin their turbines faster when the peak is there, and they slow them down or shut them down at night. We have coal-fired and gas-fired power plants that go up and down, and nuclear plants. But if we simply built electrolysis units at the power plants to absorb any extra electricity that's available to make hydrogen, then you would have, at the very peak times, you would have all of the power plant's electricity going into the grid, and at anything less than peak time, which would be almost always, you would have hydrogen and then ammonia being made basically as a byproduct of the electrical generation industry. Now, with integral fast reactors, as we talked about before, the fuel is free. So what's ammonia going to cost? It shouldn't cost very much.
Wow.
It's going to be a byproduct. So, and from a standpoint of power capacity, it's really close to diesel fuel. So, it's got to be cheaper than diesel if you're going to get it as a byproduct. I can't tell you how much it's going to cost today. Obviously, there are considerations of how much it's going to cost to add the electrolysis and ammonia production facilities to the power plants, but you can see that when you have free fuel, for the power plants, and you have essentially excess electricity that you're using to make it, it's got to be competitive.
Let me ask you this question, because with some of this technology, other industries are going to be eliminated. Your mining industry for the uranium, or we wouldn't even need coal anymore.
That's right, or oil or gas.
So, I mean, would those industries would just go away? Can you talk a little bit as far as I'm curious? I mean, it's a massive move I'm seeing over to doing this, but it seems like we're in a global depression anyways right now. It seems like this would be the technology to pull us out. Have you looked into the, I don't know, I guess it would be the conversion process of changing the way we have commerce?
Yeah, well, we can look at kind of a microcosm of this by looking at the coal industry. The coal industry used to employ really a lot of people, and since about World War II, we started doing much more mechanized coal mining. And now there's about 1/10 as many coal miners as there used to be. So, and most of those are, getting up towards retirement age because very few young people want to go into the business. So, what we've seen is over the last half century is we've seen the gradual elimination of the coal mining jobs. Although we still have a lot of coal, we just use automation for it a lot more. And so, it's certainly possible to eliminate an industry. And this is, we see this throughout history, especially throughout since the Industrial Revolution, where the buggy whip industry went out of business, and all sorts of industries go out of business, and other industries replace them. Like I say in the book, in Prescription for the Planet, where the oil industry could go into the garbage industry. It's an evolution. I mean, we have to get away from, if you believe that climate change is an issue, which I certainly do, we have to get away from using fossil fuels. And we can't just continue to use fossil fuels because we're worried about the jobs of the people in the fossil fuel industry. Those jobs will be replaced by other jobs in the clean industries. So, let's get with it if we're serious about climate change.
Absolutely. You clarified that perfectly. I mean, the horse and buggy industry did. It's definitely, I guess there's some fringe people out there that, I guess the people in the Midwest probably still use horse and buggy here and there. But now, to comment on the climate change, for anyone, I mean, for anyone because there's a lot of controversy there, but what is not a controversy is the pollution, and we can go outside and we can see oil byproducts everywhere. We can look at the Gulf of Mexico right now. So, I don't know. How has the response been? Do people are people receptive to it, or do they go, we don't need to do anything?
Well, it depends on who you talk to, but most everybody says, a lot of people have told me, don't hinge your argument for this sort of thing on climate change because a lot of people don't believe in it. And even if, and the point I make in my book, and what many people say to me also is, even if climate change isn't an issue, there are still so many compelling reasons to do this. That they stand on their own, basically. But it seems that the people who are most concerned about climate change are oftentimes the same people who are most concerned about nuclear power. And to those people, I would definitely propose that if you're serious about climate change, show me a better way. I don't know of any. This subject of the utilization of wind and solar power, and producing all the energy we need from renewables, was something that was dealt with by some very prominent climatologists who I'm happy to call friends, and they were just dismayed. They crunched the numbers for years and realized that, my goodness, we can't get all the energy we need from wind and solar and the so-called renewables, and are we doomed or what? And then they found out about IFRs and realized that, my goodness, we got it. We have all the energy we need. I would say that with people that I've had a chance to sit down and talk to about this, I've sat and talked to roomfuls of Sierra Club members who, once they learn about it and realize what this is all about, are completely in the pro-IFR camp, even if they've been anti-nuclear activists in the past.
Now, I wanted to ask a question on the IFR cost. You went over some cost figures with me that sounded like the IFR, pound for pound, was actually cheaper to construct than your average whitewater reactor. Can you touch on that a little bit?
Well, yeah. One of the things about the design of an IFR is that they're designed to be built in modules in factories rather than built on the construction site. And the concept of a modular reactor system started out with General Electric's advanced boiling water reactor, which was first built in Japan in the 90s. It was somewhat refined in Westinghouse's AP1000 design, which is now being built in China, where the largest module is 45 feet in diameter, which is a pretty big module, so they had to build this giant crane to move them into place. The PRISM reactor's biggest module would be about 30 feet in diameter, which is substantially easier to move into place. There are even smaller ones that have been designed that would be about 20 feet in diameter. But the idea is that modularization and factory construction, mass production, will, like with virtually any other thing, bring the price down. Now, the Chinese are building these first AP1000s at a cost of about $1,700 per kilowatt. And they plan to build many, many more of them, hundreds more, and to put a supply chain in place that they estimate will bring the cost down to about $1,000 per kilowatt, which is extremely competitive. Even with gas turbines, which are about the cheapest at about, I think, $870 a kilowatt or something like that. But of course, with the gas turbines, you have the cost of gas to run them. With IFRs, you won't have any cost to speak of for fuel because it's free. So when you consider that in the mix, they will definitely be cheaper. They should be the cheapest source of generating capacity of all, even cheaper than wind.
Wow, that's incredible. Now, I'm skipping around because I've been making notes as we've been talking, and there's one more point I want to ask on these three fixes for the planet, because this is the prescription. I want to cover one more point on that, and then I wanted to talk a little bit about your global energy prize that you're on the committee for. But what I wanted to ask you specifically, we were talking about some energies or some industries being phased out, similar to the horse and buggy. Now, on the plasma recycling centers, the plasma converter systems. There we go. Mm-hmm. You, in your book, you mentioned the current landfills. There were two options. One was that these plasma converters, you can scoop dirt into them. Is that correct?
Well, yeah, dirt isn't really a good source of fuel. But what you can do is you can mine old landfills. So with plasma converters, of course, we wouldn't be making any new landfills. But the old landfills are full of good fuel. So what you can do essentially is to bore down into old landfills and stick a plasma torch down there and turn it on and capture the gas that comes out. So you get the syngas out of the material. So you would be taking your old plastics and other garbage and making fuel out of it even after they've been buried in today's landfills.
So that would actually that would be keeping the oil rig workers basically employed then, going to these old landfills and actually still using their current equipment. You wouldn't even need to retool. Basically, you'd just be using the standard drill rigs. Is that correct?
No. You'd be it'd be a different deal altogether, because for one thing, you're only drilling down 100 feet maybe into a landfill. So you'd be using different types of equipment. But your point, the point you make though is a good one. One job is displaced by another. It's not like we're going to be creating less energy. We're going to be creating a lot more energy, and all these require workers. All these systems require workers. I mean, just the building of a sufficient number of IFRs to power the planet, it would be the biggest engineering project in the history of the planet by far. I mean, it would dwarf the interstate highway system. There are going to be a lot of jobs, and the thing is that when you provide developing countries with ample electricity, you're starting to create the option, the potential for all sorts of new jobs. Oop, you still there?
Are you there? Yeah.
Okay.
I don't know what happened there.
Very strange thing. So again, we can hardly continue down the path we're going in order to save the jobs that are there today. We have to move forward in a way that is conscientious and sensible and to the benefit of the planet, and understand that new jobs will replace the old jobs.
It makes sense. Now, I wanted to touch. I just lost a caller. I've had a few callers on here that I was trying to ask a question or. Yeah. Anyways, I wanted to ask a little bit about this prize from Russia. Can you tell us a little bit about that? And is it something that's been around? I've never heard of the Global Energy Prize. So could you tell me a little bit about that?
Yeah. Well,
it's a little off topic, but I'd like to touch on it.
Yeah. It's a prize that the Russians felt was. It was necessary to acknowledge transformative energy research, and the Nobel Prize, for all the different Nobel Prizes there isn't one for that. And so a group of Russian corporations initiated this, essentially what is the Nobel Prize for Energy Research, back in the early 2000s. I think 2002 was the first year. And they ask 30 energy experts from around the world to convene in Moscow every year and consider a number of candidates, and from that group we choose the winners, and the hope is, of course, that the importance of energy research will be seen as important, or if not more important, than the prizes that are given out for individual fields like physics, chemistry, and that sort of thing, like the Nobel Prize. So wow. I'm fortunate to be on that selection committee, and consequently I get to spend time with with energy experts from all over, which has considerably helped me in my own work.
Wow, that's I'm amazed there's not an award for it, but I guess I'm thankful to Russia for coming up with that. We're almost at the top of the half hour, and I don't want to keep you any longer than an hour and a half. That's how long the show is supposed to go for. Can you tell us real quick what you're looking for in the immediate future as far as, are you coming out with any more books, or where are we going with this research and development?
Well, I don't have time to write a book, another book, or even to revise mine to put the ammonia stuff in it. I'm working on the plasma converter development very intensely right now, and we're going to be seeing the initiation of this CO2 recovery system and kind of an off-the-shelf package that various countries and municipalities can buy so that we can start deploying these things in large numbers. We're hoping to do that within the next year. We're working legislatively on trying to get an IFR built in the United States, which is a daunting challenge because of the politics in Washington, and we'll see how that goes. I'm hoping that we can get Russia involved in building a PRISM reactor there. That looks like it's a distinct possibility. Even if we don't build a full IFR here, we're hoping that we can build a recycling portion of it, because we have all this spent fuel that was originally destined for Yucca Mountain, and now we decided not to use Yucca Mountain. So we need to do something with it, and what we could do is recycle it and stockpile fuel, metal fuel that could ultimately be used in IFRs, and start taking care of that problem. And then we're working on the ammonia project as well. I believe you'll see some over-the-road trucks that are going to be burning ammonia within the next year here, and kind of easing into that transition as well. So I'm busy actually making the prescription for the planet happen. So I don't have any time to write anymore.
Now, for myself or other people, how do we become involved in this? Where do we go to stay informed about this? You've got a couple of websites, and is there anywhere else, or what are those websites?
Well, the sciencecouncil.com, and you have to make sure to put the in the beginning of it, is where we have some of our information, and you can see some of the people that we're working with there. This is a question I often get asked: what can I do? Because people want to do something, and I would, it sounds corny to say, well, write to your congressman, but as legislation moves forward to try and get one of these built, we'll bring it up in the news, and you can subscribe to a News Bits newsletter at the Science Council website, so that you'll see when this comes up. And it's going to need support. Now, fortunately, there is a lot of support for nuclear power in Congress from both Democrats and Republicans, and I think, as we look forward to the next 2 years, we're going to see a lot of gridlock and stalemate, but this may be one area where we can actually get some bipartisan agreement and move forward on this. We need to demonstrate this at commercial scale, and in order to do that, politicians need support from the public. So, I would say, talk to your friends about it. Educate yourself about it. Let people know. I mean, probably most of the people listening to this broadcast have been more or less anti-nuclear themselves, once you realize that this is available and what a transformation it could make in the world, you might easily change your mind, but you've probably got 90% of your friends that are still anti-nuclear. I think the main thing is, from my viewpoint, is education is a huge thing, and I'm not trying to flog books here, but actually in my book you can find out about it. So
I was actually going to ask you to, yeah.
So
tell us where to get your book.
What's that?
Tell us where to get your book.
You can actually only get it on Amazon, but Amazon will ship it out to you within a few days, and you're off to the races. But it's not being carried in bookstores unless they specifically order it. But it's available there. So hopefully people will read it and find out more about this. So we didn't have any time for call-ins?
Well, we do. I had 3 of them, and we were talking, and I screwed that one up. So I can be honest on the air with myself and with you and with everyone listening. I kind of screwed that one up, but yeah.
Pushed the wrong button, Sancho?
Well, I had a real dilemma the other night with one of our guests. What it was is I think my mouse went dead. It was a battery-powered mouse, and that created a lot of drama because I had no control over anything. And so this is new to me, the whole radio persona, the speaking where other people can hear you. You're actually really good at this. I told you before we got on the air, you're the perfect spokesman for this. The way you wrote your book, Prescription for the Planet, and the way you present yourself, because I listened to your interviews on Coast to Coast, and you also have a Google video out there. I believe it's Google. And
yeah, somebody posted a couple of them, and there's a few more. I think you can probably find links to some of the interviews on the Science Council website as well. I did a thing at the Royal Institute in Australia, and I think those are online as well.
I mean, so you are were these technology? I mean, I have to ask because I'm looking at your book. It was written in terms that I could understand, and it answered all my hesitations, my questions. I mean, you asked about other people being anti-nuclear, and I was anti-nuclear. I thought, I don't want this stuff around. I don't want the leftovers trucked past me. In Germany just now, I'm not sure if you are aware of the train that there was tens of thousands of protesters that went out and laid down in front of railroad tracks. I think the train was coming from France, or no, it was going. I'm not sure.
Yeah, it was coming from France and going to Germany. Actually, I'm getting ready to write an article about that and about the transport of nuclear materials in general. So, I definitely heard about it.
I mean, that alone, these IFRs eliminate that. I mean,
well, somewhat. I mean, you're still going to have to move the spent fuel from where it is today. You're going to have to move it from the light water reactors to the recycling centers. So, but people shouldn't be freaked out about that. We've been moving nuclear material around for half a century, and we know how to do it very safely. The containers that they move this stuff in are designed to be, crashed into by trains and that sort of thing, and still remain intact. And the material that's in them, it's not like it's going to blow up or something. I mean, even if you were able to breach one of these casks, which is virtually impossible, it would make a radioactive mess that you'd have to go clean up. But the material that was on that train going to Germany was this fission products encased in glass, like I was talking about.
Oh, really?
It couldn't do anything. That's just a classic example of people being freaked out about something that there's no reason to freak out about. But there's a lot of irrational fear associated with radioactivity because people don't understand it. That's mainly it. And there are a lot of people who have made a living from being fearmongers about this sort of thing, rather than just looking at the science and looking at the technology and seeing that, we can move this stuff from one place to another very safely without radiating anybody on the way. So again, it's an education thing.
Now, but the IFRs, if I'm not mistaken, from just how I comprehend the technology, it would eliminate a good portion of the transporting of nuclear materials, would it not?
Well, you wouldn't be transporting actinides anymore once you get them to the plant. But you would ultimately transport the glass-encased fission products to wherever you decided that you were going to dispose of them. I was over in France back in late August, and I went to the French reprocessing center in Le Hague. And France derives 80% of its electricity from nuclear power, and the rest from hydroelectric. So they started in the 70s when they realized that they were going to need to get their energy from somewhere, and they didn't want to rely on natural gas and coal. And so they've been going now they built most of them in the 70s and 80s. So they have fission products because they do recycle their fuel in a different way. But they get the fission products and they encase them in glass, and they have them under the floor of this one big room. All of the fission products from France's entire history of nuclear power is under the floor of this one room. And I walked around on top of it. It's nothing to freak out about. We understand this very well, and we know how to deal with these relatively very small amounts of material, and we know how to safely transport it. And we would ultimately transport these vitrified fission products from IFRs to wherever we decide to put them.
You want to take a caller?
What's that?
You want to take a call?
Sure.
We've got callers back on. Let's see. Give me a second here. It's like I said, it's new to me. Caller, you're on the air.
Hello?
Hello.
Hey,
Hello.
I just wanted to thank Tom I had no idea about any of this before I heard this interview tonight, and I just wanted to say thanks. I don't have a question. He presented everything excellent. However, could you tell me, are we allowed to, with all the DMCA things, are we allowed to post this podcast on blogs and YouTube? Would that be all right?
It would be okay with me. I don't know. It's up to the station, I guess. Sancho,
it's fine with me. It's fine. It would be between you and I, or shtf11.com and you, and I'm fine with that. I think this information needs to, between the three technologies, it needs to be spread far and wide, in my opinion. So absolutely, post as you will.
It should go viral. It should absolutely go viral. But people are funny, so I just wanted to make sure that it was okay before I start sending it out.
Thanks for asking.
Okay.
Thank you, guys. Good night.
Okay.
Bye-bye.
Okay. Are you there, Tom?
Yeah. Mm-hmm.
Okay. I didn't know. Okay. For a minute there, I thought I accidentally cut you off. I wasn't sure who I cut off.
No. I'm still here.
Okay. Well, I don't want to keep you any longer. We covered the three technologies. We covered the energy prize from Russia, which now y'all award $1 million a year. Is that correct?
Yeah, but it's not real easy to get.
Wow.
It's it's like the Nobel Prize. It has to be well deserved, but it is good that this is being taken seriously and that the importance of energy research is finally being recognized. By a prize similar to the Nobel Prize.
Mm-hmm. So, yeah, that's. I'm happy.
And by the way, I might mention that the person who was the director of the two reactor sites, the EBR-1 and the EBR-2, back in the early days of nuclear power, the EBR-2 was ultimately used to develop the IFR. That person, Len Koch, won the Global Energy Prize in 2004. So this technology has been actually already officially acknowledged by the Global Energy Prize Committee.
Now, this was the man that developed it in the United States?
He was the director of the EBR-2 project, the Experimental Breeder Reactor 2, it was called. And he was also one of the team that developed the EBR-1, which was the very first nuclear reactor to ever produce electricity. He's literally one of the granddaddies of modern nuclear power. And I'm happy to say he's still with us at the age of 90 and very involved, still really lively. I just saw him a week ago in Las Vegas, and yeah, he's doing fine and still trying to help get one of these things built so that the world can take advantage of what was developed under under him and under his successors. That would have the background of the main character as this water project, and so I wrote this novel, and it was about a fictional American president, and because I was writing about this president, I had to write about something about his various policies. So I thought, I got to write a couple paragraphs about his energy policy, and I started trolling what was then the early days of the internet, and found out about some technologies here and there that I'd never heard of before, and I realized that they could be used synergistically to solve an incredible array of problems, and that started a 10-year kind of divergence from my novel, and resulted ultimately in my book Prescription for the Planet. And of course, during those 10 years, I learned about other technologies, and so ultimately, the book focuses on three technologies that can make a revolutionary difference in the life and well-being of everybody on the planet, and deal with some really serious problems that we have staring at us, like climate change, water supply issues that are going to be rearing their heads as our population continues to expand. And so, ultimately, I wanted to put it all together in one comprehensive and yet quite easily readable book for the public, because these are going to involve changes that are going to entail decisions that are very difficult for politicians to make, because for one thing, it would completely transform our energy infrastructure, and energy industries are the most powerful industries on the planet, and they won't go quietly into that good night. So I felt that the only way that we could get politicians to make the necessary decisions legislatively and policy-wise would be to educate the public about the fact that we can actually solve these problems and how we can do it, to put pressure on the politicians. I'm happy to say...
Tonight we'll be joined by Mr. Tom Blees. He's a researcher and author of Prescription for the Planet. Tom is also the president of the Science Council for Global Initiatives and sits on the selection committee of Russia's Global Energy Prize, which is one of the world's largest prizes, and it's equivalent to the Nobel Peace Prize for Power Technology. I have no doubt this award, within a few years, will surpass the Nobel Peace Prize, but I guess that's proven, waiting to be proven, but I'm feeling pretty confident of it. You can learn more about Tom Blees, his fabulous book, and his work via his website, prescriptionfortheplanet.com, and also at thesciencecouncil.com. Now, tonight, I'm not going to go over those again, but just if you have any other questions, Google Tom Blees. Tonight's program will be broken down into two segments. The first hour will be an interview with Mr. Tom Blees, followed by up to another half hour of open lines. Now, Tom has agreed to take a couple calls after the hour interview, but considering it's the holidays, I don't want to keep him away from his family all night long. So when you do call in and ask questions, please try and keep them concise and to the point. The call-in number to tonight's show is 760-542-3929. That is 760-542-3929. And on to our guest. Tom, you're on the air.
Thanks for having me. Looking forward to this.
Thank you.
And don't worry about keeping me from my family. I'm at home, so all is well.
Then I'm going to hog you to the full time maybe. No. Well, we talked yesterday, and I did. I took your time up for, probably 45 minutes, and it was a never-ending information stream of wow. That's my catchphrase, wow, and you're very impressive. Can you tell us a little bit about yourself and Prescription for the Planet?
Well, I didn't set out to write a book about how to solve the world's most intractable problems. Really, I'd started a nonprofit organization to drill water wells in villages in developing countries. And in trying to raise the money for it, I decided that I would write a novel, a political novel. Go ahead.
If we were to list out the problems, you mentioned climate change, water, and there's a few others out there that people may not quite fathom, such as, I know you have, in your book you address landfills, and what else is there? Because your Prescription for the Planet covers all of them, and it, like you said, it synergistically fixes them.
Well, part of the reason why a proposal or a prescription like this can affect so many areas is because all these things are so intertwined. For instance, if you can supply abundant energy to the entire planet with essentially limitless fuel that's already at hand, then you begin to solve an incredible array of problems. For one thing, you start solving the problems of warfare that is caused by people's competition over energy supplies. You likewise go a long way towards solving the problem of water supply for another 3 billion people, which is going to take a tremendous amount of desalination, which is going to take a tremendous amount of energy. So the energy source is a huge piece of the picture. Another one is recycling. The recycling systems that we have in place today in developed countries are woefully, let's just say they're in their very early and rather poorly developed stage. What we need is a system of solutions that don't require people to be conscientious. And I think what you see if you read a lot about renewable energy and people's ideas about how we have to change our society so that we can have enough energy and not be damaging to the environment, very often, probably much more often than not, we find people appealing to the virtuousness of humanity and sometimes proffering ways of behavior modification and that sort of thing. To my mind, if the proposed solution to a problem depends on human behavior being something other than self-interested, then it's not a solution at all, because you're only going to find a minority of people who are extremely conscientious in the first place.
Mm-hmm. What do you? So we've got these problems, and another problem is the nuclear waste that's piling up all over the world. How do we fix it? What do we do?
The nuclear waste piles are actually very small. People make it sound like it's really piling up, but there's really not that much of it. The way that we solve the nuclear waste problem is we employ a technology that can burn nuclear waste as fuel and eliminate the million-year storage problem. It might not technically be considered a million years, but the problem with nuclear waste that is very distressing to people is not that we can't safely store it somewhere for a while. The problem is that we have to safely store it somewhere for hundreds of thousands of years. Now, there is a way. There's a technology that was developed at Argonne National Laboratories in the 80s and 90s called the integral fast reactor, and it's a type of nuclear reactor that can burn nuclear waste as fuel. And if we deploy these reactors, which are extremely safe and extremely proliferation resistant, they've been designed to be proliferation resistant. The safety factor is absolutely phenomenal. If you run worst case scenario tests, which they've done, where the reactors are operating at full power and the control rods are out and all the operators die and you lose your coolant flow, the laws of physics themselves simply shut the reactor down, and they don't even do any damage to the reactor. You can come back later and start it up again. So so if you take the probabilistic risk assessment figures, which what they call PRA is a science that's quite advanced, and many technological systems that have any danger element undergo probabilistic risk assessment so that you can try to figure out, okay, is this too dangerous to deploy, and just how dangerous it is. So they've done very detailed PRA assessments for the PRISM reactor, which is the commercial version of this type of reactor, the integral fast reactor, that General Electric now is working on. And they gave these to the Nuclear Regulatory Commission, and the NRC pretty much signed off on them. And so I looked at the PRA figures, and it's interesting when you look at risk. You look at a nuclear reactor, say that the PRA figures say, well, you're going to have a meltdown once every 1,000 years. Well, that sounds absolutely safe, but you have to figure out, well, what if we have 1,000 reactors? That means that we're going to have a meltdown every year, and that's absolutely not acceptable.
It's insane.
So what we try for, the goal is to have reactors that are so safe that even if you produce all the energy that the planet needs, not just the electricity, but all the energy that the planet needs, how often are you going to have a meltdown? And so I took the PRA figures for the PRISM reactor, and I figured out how many reactors we would need to power the entire planet in the absence of any other type of energy system, and then ran the calculations to figure out, okay, if you had this many reactors, you'd have to divide that